Forest fires themselves are dangerous natural events that damage infrastructure and ecosystems, but fires leave lasting effects on the environment. After burning, soil-water repellency decreases drastically. In other words, water cannot infiltrate the soil, leading to increased erosion and flooding dangers. Post-fire soil stabilization is a key aspect to protecting burned environments and nearby infrastructure. With three main solutions used today, seeding, mulching, and laying a wool straw mixture, we set out to find how these compare in effectiveness and implementation.
Post-fire seeding was initially used to stabilize soils. More recently, it is being used to recover post-wildfire plant species, manage invasive non-native plant populations, and establish valued vegetation compositions. It is delivered typically by large aircrafts and occasionally done by hand through the National Forest Service. This can be a risky method, as the seeds take time to grow roots and stabilize the slope. One rain event before seeds have time to mature, and the seeding can become rendered useless.
Mulching is a technique that aims to increase the infiltration rate, health, and fertility of a soil. Mulch is typically made up of wood chips, straws, and other organic material. It is usually delivered by large planes, but is often very expensive.
Laying straw and wool is a fairly new technique that aims to increase the infiltration rate of a soil while also increasing the health and fertility in a more effective manner than seeding or mulching. The straw-wool mixture is a blanket-like structure that can be laid down on a post-fire forest floor. It makes it more expensive and time-consuming to lay on large plots. To compare these three remediation techniques, post-farm soil provided by Montana State University was burned for 1 minute with a torch. The soil was burned in a sieve to allow visual water infiltration. Water was poured over the soil sample until it fully infiltrated the layer. The time for infiltration was measured by stopwatch to find an overall infiltration rate.
Tested 8 variables on burned soil: unburned, burnt, tilled burnt, burnt soil with mulch addition, burnt soil with tilled mulch, burnt soil with a straw and wool cover, and burnt soil with seed addition. Due to the lack of time to experiment, burnt soil with seeds was found to be the fastest, as the application of seeds right before water addition did not change the soil properties, thus proved to be irrelevant data. With time for seed germination, useful data could be produced.
In conclusion, we found that tilling with mulch helped infiltration rates the most. To manage the cost in a real-world scenario, GIS could be involved to measure the highest risk burned areas to infrastructure. Here we created a model for the town of Big Sky, prioritizing on slope and proximity to roads and structures. As shown, this would greatly reduce the area needed to apply mulch and tilling. Further research on slope stabilization and slope modeling like this can increase effectiveness and lower costs in the future. To learn more, visit our website.